In this lecture, we will learn more about orthonormal vectors and inner products.
Now, with this we are set to another important result, and we state this as a theorem. If vectors p1, p2, so on till pm are mutually orthogonal, they must be linearly independent. So, I think before we delve into the details of the proof of the theorem, I think we have to philosophically ask this question: what really, why we need this result, right? If you were to go back to your middle school as you were plotting these graph sheets and coordinates, have you ever wondered why your xy axis had to be at 90 degrees to represent these points, right? I could also start with my basis, which is I and I plus j, and then still get the span of all the points. But what was it that made us look into these mutually perpendicular axes to represent coordinates? So, this is a philosophical question that we have to ask now, and what we routinely did in our middle school, plotting these coordinate axes and then basically looking at these graphs and etc. We have to think about it in a more deeper context when we have to get into signal spaces. And is it possible to think about signals as points in a signal space such that the coordinate axes are essentially mutually orthogonal, and this is the idea where we are sort of driving to, and therefore we need this result, okay. And this will help, and if it is mutually orthogonal, then they are linearly independent, therefore you can basically, and if it forms if it spans the space and it is linearly independent and spanning the space, then basically we can represent all the points in this space. So, and that is basically the philosophy behind how we want to approach this, okay. So, let us prove this theorem. It is probably not too difficult, standard proof. So, we start with the supposition that they are linearly dependent, and then we will try to prove this by a contradiction, right. So, let us suppose these vectors are linearly dependent. So, if they are linearly dependent, there are a set of coefficients a1, a2, so on till am, not all 0. This is very important. If all of them are 0, then of course there is an issue here, because it becomes linearly independent, because since they are linearly dependent, let us assume that there are a set of coefficients a1, a2, so on till am, not all of them being 0, such that sigma I equals 1 to m ai pi, there is a 0. So, let me call this equation 1. Okay. Now, the trick here is basically take the inner product of all these PI's with equation 1 and come up with some simplified set of equations assuming that they are mutually orthogonal, and then see if our assumption that they are linearly dependent is violating or not, right. So, now we take the inner product of one of this equation 1 over each PI. So, when you take 0 with Pi, this is basically Pi, right. So, basically what I do is sigma I equals 1. I will just take one case and it is very easy for you to think about the rest. Take it with P1. This is basically 0 with P1. The inner product of 0 with P1 is basically 0, right. And this quantity, if you simplify, now they are mutually orthogonal, and if you take P1 with P2 it is 0, P1 with P3 it is 0, so on. So, therefore, you will be only left with A1 here. So, this means A1 and the inner product of P1 with P1 has to be 0, right. Now, once you do this trick, you will get an idea for the rest of it. Similarly, A2 with A2 times the inner product of P2 with P2 equals 0 dot 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 AM with the inner product of PM with PM is 0. Now, these PI's I equals 1 to M, they are not equal to this null, which is an important condition. Not all of them are nulls, right. That is, each of these PI's I equals 1 to M are non-zero, which means now we have derived this set of equations, A1 with inner product of P1 with itself is 0, then we have these equations A2 so on till AM, all of these have to be 0, but we said that these PI's are essentially non-zero, that means their inner product is not 0, right, which implies inner product of Pi with Pi is not equal to 0. This means the only way it is possible is all of these have to be 0. Now, this means we are coming into the condition where they have to be linearly independent, which means PI's which is basically a contradiction to where we started off, and therefore this is done. Okay, so this is an important result, I think, which you should note, and the proof is very trivial, but I spent quite a bit of time in this proof because you have to get this picture very clear that if if the vectors are mutually orthogonal, this implies that they are linearly independent, and the other way round it is not possible. Is not necessarily true. That means if you find vectors that are linearly independent, then they are not necessarily mutually orthogonal. An example of this is basically, think about the vectors 1 1 and 1 0, right. These vectors are not mutually orthogonal, but they are linearly independent. But if you look at the natural basis, which is 0 1 and 1 0, they are mutually orthogonal, and that implies linear independence. So now I think with this you should be pondering in your mind, if I want to construct a basis, what is useful for me? It is easier if I go with the route of figuring out a set of vectors that are mutually orthogonal and that can span this space. So if I can do that, then I get the basis for the space, and from which I can represent vectors in that space. And it is possible to ensure that these vectors, that you can derive the set of that you can create a set of vectors that are mutually orthogonal. There is a procedure for doing that, and that we will get into the next step. Okay, clear so far till here? Now there is this notion of weighted inner products. So you might philosophically ask a question. Suppose I look at two vectors x and y, and I weigh them by a weighing matrix W, right. So I am assuming some matrix W times x is what I have. Okay. So of course this has to be, this inner product can be defined over this can be, the inner product can be a function from the Cartesian space of two vectors to complexes as well. So in fact if we think about complexes, then W has to be Hermitian matrix, but we will think about this in the context of just real entries for this matrix W, right. Let us assume that we are thinking about this, we want to define this in this way by this weighing matrix. The question is, can this quantity xy, the weighted inner product, be used as a norm? It is a sort of a natural question that we get, right. Can this be used as a norm? The answer to this is, it cannot be used as a norm simple counter would be basically, if you think about this as an induced weighted norm, where y is same as x, and then I have x transpose Wx is what I have, right. and if it has to be a norm, this quantity x transpose Wx has to be strictly greater than 0 for your W, for your matrix W, right. And trivially when x is 0, then we know that condition where it for x not equal to 0, right, for x not equal to 0, right, x transpose Wx has to be strictly greater than 0 for all x. And we cannot guarantee this unless this is a strictly positive definite matrix, right, and therefore this is an important counter case where if you wanted to extend this notion of inner product or the induced norm or inner product as a weighted inner product using a weighing matrix, you cannot think about this quantity as a norm. So I will also leave this as a sort of an exercise. It's very straightforward, to think about it. Suppose I think about this vector x to be some alpha alpha, and if I want to consider this quantity x transpose Wx, where this W is given by this matrix A B C D, and if this has to be strictly greater than 0 for every x not equal to 0, is it true for all possibilities of parameters A, B, C and D, right. Now if you just expand x, so and you take x to be some alpha alpha here, and you multiply by this weighing matrix, if you did this quantity, you will land up with alpha square A plus B plus C plus D is what you would get, right. And this quantity can be potentially 0 even though x is not the all 0 vector. So if A plus B plus C plus D is 0, or combinations of this is 0, or A plus B is 0 and C plus D is 0, individually in whatever way you want to simplify, various combinations of A, B, C, D to sum to 0, irrespective of x which is not a null vector, we land up with the induced weighted norm to be 0, which is not what we wanted, right. So therefore this is another case to think about why this weighted inner product cannot be considered as a norm. And in detection problems, when you have to deal with statistical detection under Gaussian noise assumptions, sometimes you will land up with a quantity in the exponent where you will have to look at some weighted norm of some random vectors. You will encounter these problems. I am not going to delve into this class, but if you look into statistical decision theory, there you will land up with such situations, and in such cases this metric is really useful to think about if it is going to be a norm or not. Okay. Now just an aside, can we think about expectation of a random variable in terms of an inner product, right. So, if let us look at this quantity which is expected value of x square, right. It is so if the expected value of x is 0, that means 0 mean random variable, basically expected value of x square is basically the variance, right, otherwise it is the normal second moment. So, can you think about this as the inner product of x with x under some measure which is your probability measure, right. If you think about, I mean, you sort of think about x y, two variables, and I say if I define this to be x y times this quantity, right. This is basically, if you think about two random variables x and y, and this is basically the joint density f x y of x y, this quantity is basically the joint density of two random variables, and what we are doing here is basically computing the mean, right. This is computing the mean, and can we think about this mean as sort of an inner product? If you under this measure, right, I mean, if you think about the standard inner product, you would take the product of the two functions and then integrate them over this interval, right. Now, if you bring in the notion of probability measure where you define a density function, right, can you think about the function, I mean, of basically the expectation of two random variables as some measure of inner product. I mean, if x and y, if y is x, then you have a measure of x with x, and variance is basically under this measure, it is basically a sort of an interpretation of an inner product. Okay, with these are some ideas to just ponder about.